I'm going to get started because we have a lot to cover today. So the goal with this talk is we're going to talk about probability and statistics. Who has any kind of background in probability and statistics, just out of curiosity? Great. One class counts, yeah, definitely. And this will probably be a different view of probability and statistics than you've seen before. And my goal is to try and be pretty ambitious. So I'm trying to cover like basically everything in 90 minutes. So obviously that's a lot. The real intention is to give you sort of from nothing to the generalized linear model, which is something we use all the time in statistics. This talk obviously is going to have to move pretty quickly because of that. But every other session on this track today, coincidentally, sort of overlaps with the things here. So if you're interested in any one of the things I talk about, I know there's an A/B testing talk after this. There's one on parameter estimation after that. And then there's another one on using Stan for linear models. We'll be using PyMC3 today, but you'll see that's all there. So I'll give you a few seconds sort of get notebooks and everything ready. Yeah?
Yeah, in terms of the Python requirements, do you prefer Python 3 or 2?
Yeah, there is a requirement. There's actually, on here, there is a bit of instructions if you want to install that. So this is Python 3. It will require Python 3 for this, but there's the requirements.txt should hopefully install it correctly. But it should be Python 3 if it's not specified in there.
Because I'm looking at the requirements.txt thing, is there usually like a Python equals?
You're probably right. I probably should have specified. So Python 3, yes.
Python 3 is what you want.
Yeah. And hopefully, yeah, I think you're right. I think I did not. All right. So today's talk, we're going to go through this series of notebooks split into 3 parts. The first part is going to talk, so we're going to start from 0, that you don't know anything about probability at all. We're going to talk about probability, and then from there we're going to get to what statistics is. And then we're going to talk a little bit about what's very important called parameter estimation and hypothesis testing. And then we'll introduce the generalized linear model, which is the workhorse of probability and statistics. So. And after this, you kind of get a sense of how to actually apply stats to regular sort of everyday problems that you'll come across. And okay, so let's start. So I'm going to start with this simple class right here. And one thing I want to point out in this notebook, the only thing we're really importing here is time. So there's no importing np.random or any of these libraries. We're just going to start with everything sort of transparent. And the only thing that's going to make this mysterious is time. So we have this very, very simple magic coin class. And we're going to see why this coin is so magic soon, I hope. And so you can see it's very simple. It just takes, do not leave the podium. It just takes it's a very simple thing. It takes an n, a value to initialize the coin with, and then you can flip the coin, like all good statistical coins. And when you flip the coin, it just takes time, the current time, as an integer, and modulo ends that. And if that's 0, that's the result you get, right? So just to walk through what's happening there, if we get our current time, we see it's with time in seconds from some arbitrary date in 1970 related to Unix, I believe. And if we turn that into an int, we get an int here. And then if our n is 2 and we modulo that by 2, this is actually a great example. So this number is not the same, right? So this modulo 2 would be 0. But clearly, at the time when I ran this notebook, and if I run it again, it's going to be right. So it's a little different every time because we don't see what time is. So we're going to create this magic coin, and we're going to flip it. But don't look at the result yet. OK, so this magic coin is very easy to understand. Does anyone have any questions? So if there's any questions about how this coin is set up? Because it shouldn't be too complicated, but you should definitely this coin should be completely transparent and non-magical at this point. So when we flip this coin, we get a result. And this is where probability comes in. We know exactly how this coin works. The only thing we don't know is what time it was when we called flip, right? There's some sort of state there in the world that we missed out on. And this is where we need to know probability. We start thinking about how probability works. So the coin can only be one of 2 values. It can either be true or false. And it can't be anything else. But if I said, what is the value of coin? What's your beliefs about the value of coin? True and false is not really a great set of tools. Yeah, it's fine. Overwrite that. It's not really a great set of tools to work with to describe this problem, right? We don't know. But we know something. Or actually, we know nothing in a way, right? So we know that it's either one of those 2 things, and we really don't know which of those 2 things it is. So we can think of probability as this. If we map true to 1 and false to 0, we can sort of think about probability as a softer kind of true value system, right? So we don't know the value of this coin, and a good guess for the value of this result that we have is 0.5, right? If true is 1 and false is 0, 0.5 is right in the middle, and that's literally all we know about this coin, is that we know basically nothing. It could be either one of those things. So this is an important thing I want to sort of impress on you. When you think about 0.5, you think, well, Python doesn't have a 0.5 type, a value. That's not like a Boolean thing. This is a Boolean type. It can either be true or it can be false, but it can't be 0.5. And this is actually a really, really important thing about how probability and statistics work. When we make statements about probability, we're talking about probabilities in our mind, okay? So it's true that the result has not a 0.5 value. 0.5 expresses what we know about the state of that result in that coin. And so we have this clear picture of the world and how things work. We know exactly how the magic coin works. There's no randomness out there. Randomness is just because we're ignorant about the current time. And so I always think, if we think this way, it kind of makes a lot of probability problems clear. So Nassim Taleb has this famous book called Fooled by Randomness, right? And when we think about fooled by randomness, we think about this randomness that's like out there in the world, this sort of chaotic force. But when we think about randomness as a statement about our minds, this title seems much less shocking, right? So if we write this to say, fooled by the ignorance of the full nature of the processes influencing my life, this seems quite obvious, right? When you think about it that way, you go, yeah, of course. Another example I always like thinking about is, Einstein's favorite quote about Heisenberg uncertainty, right? He says, God does not roll dice, right? And that's when you think like, yeah, the universe can't be random. It can't just be chance. But when you think about that as a statement about knowledge, Heisenberg sort of says, well, there's a limit to how much we can know about the universe, right? So you could rephrase God doesn't throw dice to saying something like, we cannot, there's a limit to the full intentions and actions of God that we can know, which is a much more kind of obvious statement. So in general, when you're doing probability and statistics, and actually the deeper you get into it, the harder this temptation is to sort of think of randomness out there. We think of like normally distributed random variables, all these things, and we think about that as being probability out there. But probability is always in here. And in general, when you keep that in mind, you make much less statistical errors when you're trying to solve problems. Okay, so now that we have this, we can look at the result. And every time you run this, it's a little different, which is kind of cool. So this is false. And if you all have the notebook up, you can run it. And obviously, some of you will get true. Some of you get false. And now probability is gone. We know exactly what happened. We know the time was even when we called flip. And we have this result in our hand. So that's sort of the basic idea of probability as like a single value. But the cool thing is, because we mapped probability to Boolean logic, we actually now can start thinking about, can we do other logical things? So as programmers, we're very familiar with Boolean logic to solve all types of problems. We've got not, and or are like foundational tools that we use as programmers, right? We can use these same tools as probabilists. So in logic, we have not, and not is this sort of simple negation. I mean, we all know this, but let's just walk through it. Not true is false, not false is true. And if we want to make this probabilistically, we just say, so not in probability is just 1 minus whatever the probability of our thing is. And this works perfectly fine for the case where we map probability directly to truth, right? If we just want to replace Booleans in Python with probabilities, it still works just fine, right? So 1 minus 1 is 0, which is false. That's what we want. 1 minus 0 is 1, which is true, which is also what we want. But now we get this extra flexibility here. We can say things like 1 minus 0.25. And now we have a negation. So we have this more powerful negation that's a bit more flexible that we can use for other things. We also get and. So we have true and false. We know is false because they both have to be true, right? True and true is true, and false is false. We have a probabilistic and. Oh, one thing I should note is if we get into something called conditional probability, which we're not going to talk about today, these definitions just get a little extra extension to them. So this is the case when two things don't depend on each other. Information about one doesn't change. Just know that you may see variations on this that are a bit more complex, but don't worry about that for this point. So so in probability, we make and is just multiplication. So we can combine two probabilities that we will see if they both happened using and, which is multiplication. So again, this works exactly the same as regular truth tables, right? So true and true is true. True and false is false. False and false is false. But again, we get this great extension where we can say I'm not sure and I'm not sure. So 0.5 and 0.5, and I get 0.25. So I get this way to combine my uncertainties in a logical way. And the last logical tool we have is OR, right? So, and of course, you can derive XOR and all these things if you wanted to. But OR is a little bit more complicated because of the math behind it. So OR we know in logic, right? OR is true or false is true. True or true is true, obviously. True or false is true, and false or false is false. So as long as one thing is true, it's true. Now in probability, this is actually a mistake that's common. People make this. So they think, okay, we did multiplication for, and if we just do OR, we can add them all up, right? The probability of rolling a 6 or a 5 or a 3 on a dice, you just keep adding those up. But what happens in practice, and we don't have time in this slot to go into it, is you'll end up actually overcounting if things can both happen. Like flipping a coin heads, rolling a 6. So we need to account for that. So we have this little extra term here. So there's the probability of event A, probability plus the probability of event B, minus the combined probability of both of those events. You don't have to know deeply why at this point, but just know that this is the actual rule for OR. And again, if we just replaced Booleans in Python with probabilities and replaced OR with this, it would work out. And so we see 1 plus 1 works out because it's 1 plus 1 plus 1 minus the probability of 1 plus 1. 1 times 1, right? So that's going to be 1, which is great. That's what we want it to be. And you notice if we didn't have that term that multiplies and takes that away, we'd be overcounting. We'd get 2. And probabilities are between 0 and 1, just as a rule that we have. So that would not be good. So this works out, and we can see 1 and 0, which is the same as true or false. We get what we want. We get true. And of course, we get 0 if they're both false. And then again, we get this extension where we can really ask more complicated things. What's the probability of an event that we're 0.25 sure of happening, or an event that's 0.3? We can do the math, and we can get it out. And we get an answer for that. OK, so these are the basic rules we can have. And so now we have this whole framework for dealing with uncertainty. Oh, great. Perfectly on time. Which is great. So we have this thing where we have this random result, and now we can start thinking about how we can combine all of this things we don't know. And this is actually very powerful tools. You can take this, and if there's a lecture stop now, you can sort of work it out on your own and solve a ton of problems. And we're going to see an example of that next. So we're going to make another magic coin. So logic, these are 2 points I want to drive home too, as well as logic is how we reason about facts, things that we know for sure, and things that we don't know for sure, we use probabilities. And obviously in the real world, almost everything we don't know for sure. There's always some little margin of uncertainty around basically anything. So we're going to create a new coin, and n for this coin is going to be 3, right? So that means if the time when I flip this coin is evenly divisible by 3, we're going to get true. Right? Last time it was evenly not divisible by 2, it was true, so it was even. So every third number is going to be that. So we want to come up with a probability for this sort of intuitively, and this is the correct answer as well. The intuitive probability for this is that, okay, so if I just pick some numbers, 1 out of every 3 is going to meet my condition, so I'm going to say it's a 1/3 probability that I believe it's true. Okay? Is everyone following so far? Good. So again, we can go into deep philosophical discussion of how we prove that this is true, but in this case, your intuition is right. 1 out of 3 events is the one we care about. That's going to be true. OK, so now we're going to do something a little bit more complicated here. We're going to create this results list. OK, and we're going to create this, and then we're going to append this new magic coin to it. It's going to flip it. One thing that's interesting is because it's using time, if you put these all in a single cell and run them at the same time, they'll all be the same because it all happens at the exact same time, right? Like within a second, as far as Python cares. So when I first built this out, I was like, oh, why is it always true or always false? I'm like, oh, yeah, because they all execute in under a second. Which actually is a good point about when you think about the more we know about how something works, the more we can reason about what we don't know, right? So you know if they're all in the same cell, they're going to be the same. So if we wait a few seconds, and if we run this one, and now we have another probability question. Okay, so this is a bit more complicated. Before, I just wanted to know whether or not the result was true. Now I want to know what this Python statement is going to evaluate to. And so we've added 2 things to a list, and we flipped them at times. I don't know what times they were. And now we have 2 results, and I want to know the result that is any, right? So we're going to walk through how we're going to reason about this, but just sort of think about how much information. This is a minorly more complicated case, but it's gotten a lot trickier to sort of reason about how confident we are in that. So the probability of true is 1/3. We flipped the coin twice, put them in there, and if any of them are true, then we're set. But we have to sort of think how this works. So we can think about all the possible things that could happen. In general, if you're not sure where to start with probability, counting out the outcomes you want, looking at the outcomes you care about, is a good way to come up with your probability. So again, we can prove that in all kinds of fancy ways, but this is a generally good rule. And it's tricky when you can't count outcomes, like probability of weather tomorrow being rainy. Those are a little bit more sophisticated ways to think about it. But for this, we can just list out all the possible outcomes. So these are the things that could have happened, right? We could have true or true, false or false, false or true, true or false. There's 4 outcomes, and we just need to know the probability of the ones that we actually care about, which is true, true, false, true, and true, false. So we can actually use our logic of looking at this. So we know that the probability of true and true, right? So we can just enumerate through all these, look at the probabilities, and we can just use our basic logic, right? So we want to know the probability of true and true, right? So it's just a logical statement. We can use our rules there. So the probability of true and true is 1/9, right? Because we went through those rules before. It's 1/3 times 1/3. Now we have 1/9. That's how sure we are that that outcome happened. Then we have the next outcome we care about, which is false. So we can actually go through all of these. So we know the probability of false is just the opposite of true. And we can use the logic for this to figure out that the probability of this one is 4/9. Okay, and again, this is, it's okay, if the math is like boring you over at like 9:30 in the morning, it's totally fine. You just have to remember that this is, we're just doing the and ors and nots that we just went through, the basic logic there. So there's really no, like the equations can make your mind feel very tired, but this is really just the application of that basic sort of logic we had. And then we have these other 2 outcomes that we want, which is the true and false, and this flip is going to be the same, right? So this is true and false. In this case, we get 2/9. And so we can put the outcomes we care about are true, 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 false, or false, true, right? So those are just there's the 3 outcomes that we actually care about, and we just don't know if any one of them happens, so one or the other or the other. And since they can't all happen at the same time, we don't actually have to worry about overcounting, so we can add them up, and we get 4/9, okay? So one way to look at this is, okay, these are the outcomes we care about, and we're just going to OR all of them and see what we get, and we get 5/9. Another way we could solve this is you could say, wait, we know the probability of false and false is 4/9. All I care about is what's not false over false. So that's going to be 1 minus 4/9, and it works. The point I'm showing here is that this is consistent, right? You can express the OR of all the possible outcomes we care about, or the negation of the outcome we don't care about, and both of those should be logically consistent, and they are. So even though there's a lot of sort of calculation happening here, it's really still boiling down to basic logic, which is pretty cool. Now we get something really powerful out of this. So let me actually just see what the result is, because I always like seeing what happened. It happened, great. So this is cool, and let's try one more thing. So that was already a lot of work, and we just had 2 things in our list. Oh, time is going excellent. So we just had 2 things in our list, and already I can feel like everyone's brains are like, all right, this is pretty good. We're going to make a more tricky one. So this is our 3rd magic coin. And it's initialized with 4, so it's going to be probability of 1/4. And we're going to flip it, and we're going to flip it again, and again, and again, and again. All right. And so, wait, what was the idea here? Oh, yeah. So we just want to, oh, yeah. So I want to see what the length is, all right? So this is much trickier. So, so the question I have is how long is it? I want to make statements about how many things are true in this, right? So we're going through there for each. If it's true, it's going to return true. And I want to see how long that is, right? So we're filtering. So we flip this 1, 2, 3, 4, 5 times. And I want to know how many times it came out true, right? That's my result 3. So the question now is, what is that number? And this gets really hard really fast, right? Even though we're just dealing with these rules of probability, these logical things, it's really tricky. We can't go to our old solution where we enumerate all the outcomes, because we've got a lot of outcomes now, even with just 5 coin tosses, right? We've got 5 things in this array. I just want to know how many are true and how likely that is. How likely is it that 2 are true? So this is really, really tricky. Thankfully, we have a probability distribution for this. So this, we're going to import SciPy's stats, and we're going to use this binomial distribution that they have. And this distribution, we're not going to derive it from scratch, but it basically, we actually did. So what this distribution does is it does this work for us, where it enumerates the possible outcomes, and then it counts how many trues there could be and the probability of each of those, right? So we're going to walk through this distribution, but the binomial distribution is just a function. You can think of it as like a regular Python function that you tell it the probability of an outcome happening, you tell it how many times you flipped the coin, and then it will tell you for any given input how likely that is to happen, what the probability is for you. And it's doing it the same way we calculated this, it's just that you don't have to do this by hand anymore. So we can see, so this was, oh actually this should be 1/4. Anyway, if we did, this is for the first example. So in this first example, we had n is 2, right? We had the previous one, we had two things. Each one had a probability of 1/3 of happening. We can actually have it do the math for us, and we get this. So this is the same thing as the 4/9 that we expected. So this is the probability of getting no true with 2. This is the probability of just getting 1. And this is the probability of getting 2. And we can add these two together. So this saves us doing all the work we did for that first part. So if you did the first part and thought this is really confusing, I don't really want to do this much kind of probability, you don't have to ever again. Now that you've seen how you build that up, you can use the binomial distribution to do that work for you. And it's really important because we need to be able to do that to solve the problem we have now. So we're just going to look at what this looks like, where we have 5. So this is the distribution for 2. So this is actually this is visualizing what this distribution looks like. This is the binomial distribution for that previous example where we had 2 coin tosses. So the probability of getting 0, 1, and 2 true values in that array. Now we have 5 tosses, so this is our problem now. This is why we really need these distributions, because even at 5, this problem has become really, really hard to do with pencil and paper, to sort of just think through. So we need these tools to solve this problem for us. And we're going to do this for 5. Get this distribution, plot it out, and you can see what this looks like. So this is really useful, because now if I ask you, and we want to look at it, but if I said, what's the probability of getting just one true value out of that list? What's the probability that the result 3 is length 1? You can look. You can go, oh, it's going to be about 0.4. Is it likely that all 5 are true? No, it's almost not going to happen, right? Is it more likely that I have 0 or 2? All these questions can be answered with this distribution, which is really useful. So yeah, so we can see what's the probability of getting 1. We can get that exactly. We can look at, if we wanted to know what the probability of all these sort of other values, right? I want to know that it's greater than 1. I can get the sum of all the values greater than 1 here, all those things. So we can sort of start reasoning much more in complex ways about this thing, which is really hard to do the probability for, because we have this distribution. Okay, so this is the binomial distribution. That's going to be the end of this part. But let me get you to where we sort of start thinking about the difference between, actually I want to know what the result was. 1. So this time we got just 1. So this is probability. And so I think a big thing people question is the difference between probability and statistics. And so probability so far, we've known everything. We know exactly how the magic coin works. We know exactly what parameters are in it. It's completely transparent. We just have one tiny piece of information we don't know, but we have a very clear understanding of how much we know and what we don't know. And so we're able to do these things, and even though it's a bit of work to do all the probability, we can still work through it. And now that we have tools like the binomial distribution, we can ask all kinds of questions and sort of get a better sense of this. So this is a slightly different variation on our magical coin. This magical coin is initialized with a value that we don't know what it is. So I took the time, right, and I made it an int, same way the inside logic does for this. I added 1 to it, so it's not 0. So this could be anything between 1 and 7 is the value that this coin was initialized with. But we don't know what that is. And so now when I do something like this, if I just put 3 in here, it's really hard to make a guess what's in there, because we don't know anything about the coin. And this is where we actually need to sort of flip our thinking around. So before, when we were thinking in purely probabilistic terms, we were asking questions about what data should I expect given that I don't know, right? What's the probability I get ahead or a true value, right? What's the probability I get 3? Those types of questions, right? We know how the machine works. We know how the object works. We want to make an assumption about how the data comes. Now, we're going to use the data to start making assumptions about how this model is working. And that's sort of how statistics work. That's why there's the data in data science. Because we need data to understand it. Without any information, you don't know very much about this coin at all. It could be anywhere from, if the value is 1, every result out of this coin is going to be true. If the value is 1/7, it's going to be very rare to see trues. The difference between 1/7 and 1/6 is not so big, so it's going to be hard to see. And so we can look at the results in a second, but this is sort of the visual I have for where we are now, right? And we have probability. We have a very clear view of the world, and we have a very clear view of what we don't know. In this case, even for this very simple example, there's not a lot of moving parts to this, right? When you think about the world that we try to learn about as data scientists or programmers, there's a lot more unknowns going on. In this model, there's not that many moving parts, but it's still very hard to reason about. You could do that, and I have homeworks at the end of these if you want to sort of really dive deeper after the talk. But this is where we are now, right? We don't even really know what we don't know. We don't even know how we're going to necessarily tackle that problem. And part of it's because the world is sort of hidden from us. And that's the real life problems we have all the time, right? You want to know whether a product is selling better on your website. There's a lot of information you don't know about who's viewing that, what makes that product successful, what makes someone buy a product. And we're going to do that in the next section. We're going to look at that a little bit deeper. So we can actually look at these results. Actually, I'm not going to rerun this one. This was an interesting one. So there's one outcome in this magic coin where if it's 1, the magic coin is always going to produce the value true, right? Because anything modulo 1 is going to be true. So if we get these results of our new magic coin, right? Our new magic results where we don't know even what it was initialized with, this gives me some evidence that there must have been 1, right? The value in the coin, it could have been like 2 or 3, probably wasn't 1/7, right? It probably wasn't 7 was the time that I ran the coin at, because if that was the case, then it'd be very, very unlikely to get true, right? We're not going to do the math for this, but you can start thinking, this is how you start thinking statistically, right? Given that I saw this, now what do I know about plausible explanations for what's happening inside that coin? And that's, when you think about how we do business problems, right? That's what we're always trying to get. We're trying to get a plausible explanation for what's happening out in the world. We don't really know what the real world is a much more complicated version of the magic coin. And what we're trying to do is take the data from the world and try to interpret and get a sense of what's happening out there. And so when we run this again, you can see in this case, and you can intuitively feel this, right? If you get this many true results, you can at least, I think everyone here sort of feels like it should probably be 1. Because even if it was a 2 was the initial value in there, right? It's really unlikely that in 6 coin tosses, you're going to get all heads, right? You can just sort of feel that. You can work it out mathematically. That's what statistics is about, is actually putting numbers to that. But here we can tell, I'm pretty confident that this is a value of 1. So the homework for this, if you want to do this, is you can actually just sort of explore this. If you really understand this last example here, this sort of statistical example of the magic coin, then you really understand all of statistics. So this seems like a trivial problem, but if you sit home tonight and you sit home this week and sort of start thinking about how this coin works and trying to unravel it, you can work out the probability from the very beginning, because you can look at the probability of each time. You can think of what possible outcomes those would give you, put that all together. It's a very complicated thing. This is not an easy homework. But if you really want to dwell on this and sort of get an intuition for how probability works, diving into this problem deeper will really help you. And it's hard. So if you feel like, wow, this is tricky, it is, because it is actually tricky. And then answering questions like, okay, so how many coin tosses do I need to make a good guess, right? And can I know, like when it's all trues, we can make that guess pretty quickly, right? We know that I'm pretty sure that that's 1 inside that coin. And because it's an object in Python, you can actually peek inside, right? You can see what that n is and see if you were right. But as you start answering those questions about how you'd make inference about that coin, that is what statistics is. So that is how we think about statistics. And if you really understand how you would run tests on that coin to make a guess, how you could differentiate between whether it's 7 or 6, which are the really hard cases there, what possible values it could be, how you would do all that. If you can build that all out, you basically understand all of statistics, in my opinion. You have really the core part of it. And you don't need any more tools than what we have right here, which is pretty cool. Okay, perfect timing, halfway through. How's everyone doing? Does anyone have any questions on this first part? Great. I really appreciate everyone coming here in the morning to talk about statistics. Like it's after a conference, like that's really, like I'm proud. So now we're going to move behind the scenes. There is going to be some random here, but you're not going to see it directly. And this is going to get into a really important idea of parameter estimation, which is what we just were sort of talking about. So here you'll notice I have a couple of classes that I developed. I'm not going to show you how they work because it's part of reality and real statistics. If you want, when you look in the repo, you can actually look how these classes are written and sort of see how they actually work. They're not that complicated. They're not much more complicated than Magic Coin, but we have a customer, a product, and we run an experiment. So the product class has it has a quality number between, well, it's not enforced, but it's between 1 and 5 in the examples, and it has a cost. And those are the 2 basic things, right? So it's a very simple product, and when a customer interacts with the product, they can choose to buy it or not. And the customer has internal preferences for these things. And it's totally deterministic. So the customer, that's one thing I can tell you about this. When the customer buys a product in this example, it's not random. It's completely deterministic. If you know the internal state of the customer, you can absolutely decide whether or not they will purchase the product. It's not this randomness out there. All the randomness, again, is inside our heads because we don't know how this all works. So here's a toothbrush. It's an all right toothbrush. Costs $4.99 and its quality is 3.9. Now, again, in the real world, this is interesting. In the real world, if you have a product, you don't actually get to input what the quality is, right? That would be awesome if you could. If you could build a product and be like, we're only going to build perfect products, that would be great. In this example, we have that. Well, you do have control over the price in real life, right? So this is where, like, you even get, when you start using more and more statistics, you start asking questions about, like, what do I even have control over? How can I make this toothbrush do better? But in this case, in this happy world, we can choose the quality of our toothbrush, and this all right toothbrush is all right, and it's not too expensive. And what we can do is we can take this and we can get a random customer. And again, a customer will deterministically buy this product. They're generated random. So this customer represents, if you have a website, or I mean anyone that's doing anything with people, this represents someone that walks in from the street or comes to your website randomly. You don't know everything about them, right? There's a lot of details about that person, and we're completely ignorant of what those are when they get there. But they are sampled from a population of people and they come. But this is an actual instance. This person object is an instance of a person, and their preferences are fixed once they're created, and there's nothing that, we don't know what they are, but they are set. And we just decide whether they'll purchase a toothbrush or not. This person did not decide to purchase a toothbrush. So this is great, right? And we don't really know anything about the toothbrush. The funny thing is about this, though, is, so we're going to build an experiment to do this. But the funny thing about this toothbrush is it's actually much more complicated than the magic coin. But one of the great sort of mercies of statistics is that the more complicated things are, the sort of broader assumptions we could make, right? So we're going to just sort of think about this as there's going to be some kind of rate that people buy toothbrushes, right? There's some kind of probability that if we show a toothbrush to a customer, they will buy it. And this is something we do all the time in real life, right? I mean, I work at Wayfair, and a huge part of my life is figuring out what's the probability that a product will sell if I show it to a bunch of people, and why. So this is, and so we're going to, but when you think about it, that's a very simplifying statistical assumption, right? The reality is this toothbrush has these thresholds, this customer has these thresholds. When they match, the customer purchases it. We're not modeling that. That's a lot more complexity. We're just going to make the simplifying assumption that it all kind of works out in the end, and there's a rate that if we show this, we will sell it. So we're going to design an experiment. There's an experiment class, and what this is going to do is it's going to show it to a bunch of customers. So we're going to run a test. We're going to show it to 20 people, and we're going to try to figure out what is the rate that this coin sells. And again, we're in statistics land now. We're going to use probability, but the first talk is really the only part that we're strictly in probability space. So this part, and here on out, we're trying to look into this object and try to understand how it behaves. And in this case, there is no magic end that we can actually peek at and tell us how it works. So we get 20 purchases. We can see some people did, some people did not. Even looking at this, you can kind of make some intuitive feelings for how well this toothbrush does or does not sell. So, and again, this is not like the magic coin. This is a black box, right? People talk a lot about black boxes in machine learning, and I think one thing I also like people to think about is the reality is actually the black box. It's not neural networks, right? The real world is the thing that we don't really understand, and we're trying to take a stab at it, and this is sort of an example of what we're trying to do. So we showed this to all these people, and we can see in this case that 6 sold out of 20. So in obvious first, if you saw this data, you'd say, okay, 30% of people will buy this toothbrush, right? And that's a pretty good, we call that in statistics a point estimate, but it's a pretty good estimate. But given what we've seen, are there other options, right? Is there other possibilities? And so, of course, right? I mean, our best guess right now is our intuitive guess is that it's a 30% chance to sell. But we could just, what if we changed our estimate by adding 0.05 to it or subtracting 0.05? Are those possible? Of course they're possible, right? But how do we quantify that? We need some sort of way we can say how possible they are. So when we think back to the binomial distribution, right? We can say, oh, actually, so if we knew, right? If we knew this estimate we have, this 0.3, right? We know how many people we showed it to. That binomial distribution will tell us how likely that outcome that we actually saw was if that was true, right? So if the rate is 30%, and we go back to probability land where we assume we know we are correct, we are at 30%, how likely is what we saw to have happened? And we can now get a number for that. This number in a vacuum isn't super useful, right? This just tells us which of the possible ones. What we can do is we can use this as a tool to compare other guesses, right? So if I were to subtract from my estimate 0.05, we can do the same thing, and you can see it's less likely, right? If that was the true rate, if 0.05 less than what we observed, what our guess is, was the true rate, then it's going to be slightly less likely, but certainly not impossible, right? It's a 20% chance with our best estimate, but these other estimates that we have, we can add to as well, right? So of these estimates, we can see that adding 0.05 to our estimate is a little bit more likely to have produced the data we saw than if we subtracted 0.05. Both of these are fine though. So which one is it, right? We don't really know. And so this gets to that sort of modeling our internal state of what we believe. So we have three options here. I know my best option, but I don't want to be constrained to just one possible option. So we could think about this if we did this idea, right? Of just okay, let's look at the binomial distribution. Let's iterate through a bunch of possible outcomes, right? So in this case, we're just going by every 0.10 guess, right? Like what if it was 20%? What if it was 50%? We get a distribution that looks like this, right? So our 30% is that peak right there. That's our best guess. But you can see how well every other guess we could have made describes it. So it's really, really not possible looking at this that it's 80%, right? If I said, I think this toothbrush is great, I don't think it's just an okay toothbrush. I think this is an amazing toothbrush and people love it and they really are going to buy it at 80% and we just got really unlucky. You would go, I don't think that's true, Will. It's really unlikely that this toothbrush is that good and we happen to get with 20 people this outcome. And you can say, yeah, but Will, there's all kinds of other guesses we could make here, right? And so we can do that. So we can keep making this more and more fine-grained, right? We get a smoother and smoother curve and we get this beautiful, you're doing math when you get these really beautiful smooth curves. That's real life never looks like that. So now you know you must have done something smart because you got a smooth curve. So this is where we want to be, and this introduces the other distribution we'll use today, which is called the beta distribution. We're definitely not going to derive how to get there, but this is the intuition behind the beta distribution. The beta distribution is a very fancy sounding one. It has two parameters. It's a little confusing. So it has two parameters, which is alpha and beta. And alpha is how many successes you had, so how many true values, how many sold. Beta is how many you didn't, which means the total is alpha plus beta. So a binomial model, right, we had how many successes you had and how many total. When we do the beta, we always look at successes versus failures, and we have to add them together to get the total. This distribution is a continuous distribution, which for all that's practical for this talk, this means that it goes over every possible rate that we could have. And it also is scaled a bit differently so that when we do math on it, it all sums up to 1 to get a complete probability. But this is basically what it looks like. And this is really useful because this now, you remember that sort of fuzzy image of our brain? We didn't know statistics. So for this toothbrush problem, this is now the clear image of our mental state. This is what we actually believe. And when you saw those toothbrushes, you don't necessarily feel that, right? When you just see, okay, I see 6 sold out of 20, I don't know what I believe. This is the correct, and there's some tweaks we can do on this. I don't want to be too dogmatic. But this is sort of the correct model of your mind, which is a really useful tool to have because now you can start doing quantitative things. So this lets us do, this is my favorite part of this actually. So normally when you get introduced to this, you have to do calculus to solve this and everyone's like, okay, I'm out. I don't want to do calculus. But because we're all Python programmers here, the best thing is we can just sample from this, okay? So this is, we're going to use NumPy, the random beta. This will sample from this distribution that we have here. And you say, okay, so what do we do with that? The cool thing is we can just ask questions about samples and they'll give us the answers we want, which is really, really good. And it's not even a hack, it's the way you have to do it when you get to really hard problems. So you don't have to feel shame for not doing math. You can actually feel like you're a sophisticated person doing a Monte Carlo simulation because you are. And if some math person tells you, oh, you can't do it, you gotta really do this by hand, you can say, no, you don't, because once you start getting into real problems, which you'll have a couple of speakers today talk about, when you get to really complicated things, you need to use PyMC or Stan. They are doing a very, very, very sophisticated version of this. But at the end of the day, we can only solve these really hard problems. So this is the way to start thinking. Start thinking in terms of samples. It's not a cheap trick. It's actually the way we do it professionally. And the cool thing is now you can encode, ask all these great questions. Okay, so what's the probability that the rate is actually greater than 0.4, right? Given that I saw this, is it possible that it's much better than I saw, right? We saw 30%. Could it be 40%? Now you can actually put a probability to that. So you just literally like ask that question of the samples, right? How many of these samples are greater than that? How many samples were there? That's our probability of that happening. That's really cool. Normally you'd solve that by integrating over the distribution. You don't have to integrate ever again now that you have Python. And then of course the nice thing is, this is sort of confirms this. If we look at the samples from this distribution, I put that math in there because you just got to put some math in these talks so you feel legit. But you can see when we estimate this, right? The mean of these samples is the same mean we came up when we did this empirically, which is just sort of a good sanity check that when we take a whole bunch of samples, the average of this is exactly what we estimated for that. And that's because that is that's what that math says, that the expectation of the beta distribution is alpha over alpha plus beta, which again, alpha plus beta is the total. So it's just how many you saw over how many there are. But it's like a really fancy mathematical way to say that. So if you like are just averaging over what you saw, you can just show people that and they're like, wow, very sophisticated. Okay, so now everyone's favorite thing, hypothesis tests. This is actually what got me into Bayesian stats because I hate t-tests and I hate p-values and nobody understands them, and people who tell you they understand them are going to have someone else that tells them that they don't understand them because they're silly, and we're not going to have any p-values in this, okay? So the cool thing is we already have this great framework for hypothesis testing. So we're going to introduce a new toothbrush, the luxury toothbrush. This is a great, great toothbrush, but it costs more, right? Again, it's nice to be able to control that quality. So the luxury toothbrush is another toothbrush, and it costs more, it's better. The thing is, how is this going to perform when we try to sell it? The cool thing is when I wrote this code, I actually had no idea how this is going to work. So even I did not go, this is the answer. That's why I actually didn't sample from distributions for this. I have this actual little behavior in these models. They're really deterministically deciding things. So even I didn't actually know how this was going to work. I wasn't like, we're going to sample from a normal and I know the answer. I don't know the answer. I mean, I do now because I did this talk. So our experiment class has this nice ability to take 2 products in and it will run an A/B test, which just means we're going to show, when we run experiments now, rather than showing one product, we're going to show the 2 products to 2 groups of people and get results from both. There are 2 separate groups of people, but we just assume that they're randomly distributed from that same group of customers. Just random people come into the website, we show them different toothbrushes, see how many buy them. So we're going to do a test with 30. These are actually kind of fun. I'm afraid it's going to blow up already. But yeah, so this is a test with 30. We're going to show it to 30 customers. And we can see, we know how, so the A purchases, the first argument there is the product A, and the second argument is the product B. It's an A/B test. There's going to be another talk today on A/B testing in depth. So if you like this, you can go to that and get sort of a much deeper dive into this. But here we go. We got all these values for this, and we get the luxury toothbrush. Looks like it sold a little worse. We can print this out. Okay, so we do see this. And this is where parameter estimation comes in, because you might see that and you go, why do I care about how certain I am about toothbrush selling? If it's 30% of the time, it's fine. But this is where it really becomes important, because now we have these 2 estimates, and we want to know how likely is it that I'm wrong, right? So if I look at this, I say, okay, the cheaper toothbrush sells a lot better. People don't care about quality as much as they do price. They're much more price sensitive than they are quality sensitive. All I care about is I look at this, I'm done. But that's why we need statistics. You could be wrong. If I did this as 2 toothbrushes, you wouldn't believe me, right? We only saw 30. We only gave it to 30 customers. Do we have enough information to know? Are they different enough that we can? So what we can do is this is just a lot of stuff for plotting, for running this experiment. We can plot this out. So we can plot these 2 beta distributions, right? So each of this is the estimates from the data we got for each of the toothbrushes. So we have the luxury toothbrushes beta distribution there, and the regular toothbrushes over there. And you can see there's a lot of overlap, right? So these are how we believe about each of these, but we can see our beliefs kind of cross over a bit. And we're not quite certain that all cases of the luxury toothbrush being worse are true, right? We have it could be possible, based on what we've seen, that the luxury toothbrush really sells at 20% rate, and the regular toothbrush does at 10. Those are both pretty reasonable beliefs. There's a lot more, obviously, in the other one, but we can solve this. We don't have to do any fancy math. We can run larger tests, and that's the cool thing. So as we run this larger, we get better estimates, right? So this is the classic, why is data important, right? As we add data to this, these estimates get more and more narrow. So this time we looked at 100 people, and we can see compared to this first one, this one we're kind of confused. At 30 people, there's a lot of overlap between these 2. At 100, it starts to separate out quite a bit. There's still that little tiny area. We kind of want to be nervous about that. But again, we can do the same thing with samples, right? So this is a really tricky problem. We have to sort of look at 2 random variables and the differences. No, we don't have to do that. We can just sample, and we can ask questions of the samples. And so we can literally say, okay, we're going to take 10,000 samples of each of these distributions that we have, and what's the probability that, let me just run this again. Yeah, so in this case, for this one, it's very unlikely, right? So, because they're quite separated. But we want to put a number on how separated they are. You can't really tell. So what is the real probability that the luxury is in fact better? Or in this case, I'm going to look at the probability of, you can look at the code, right? So I want to know the probability that the regular one is better than the luxury one. So you can literally just code that in. You take samples from your distributions, and now we get an answer. And so if someone says to you, okay, we ran this test with 100 people. Are you sure that the regular toothbrush sells more? You can say, yeah, I'm very sure. I'm 99.5% sure that that toothbrush sells better. And you can really be confident. And you built this whole thing up from scratch. So there's no magical p-value. Like, yeah, I put it into t-test, and it gave me some p-value. I don't really know what it means, and I hope I did it right. You can reason through all of this. We built all of this up from basic logic. We had to throw in a little extra math for the beta distribution. But now that we have that, we're here. And so you can really feel confident about this. And again, you can keep sampling and ask kinds of questions. If you want to know, okay, but what about this or that, you can tweak this a lot and play with it, and you can build any experiment you want now. So the homework for this section is to sort of, I have a post on this that goes into a bit more detail. There's ways that you can add prior probabilities to this, which is really interesting. I'm not going to go over that today. The blog post there does go into it quite a bit. It's actually very easy to add a sort of prior belief. Like you might be an expert in toothbrushes and say, Will, I know that these luxury toothbrushes are going to sell. I don't think that 100 is right. I think that this toothbrush has got supremely unlucky. As a toothbrush expert, I recommend you take my advice. You can actually incorporate that into the estimates, which is very cool. Let's see where we're at. Oh, great. We actually have a little bit of time. That went faster than expected. Wonderful. Does anyone have any questions about this part so far? No questions. Great. Wow. So we're going to actually succeed at this. Let's see if part 3 works. Oh, this is great. Okay, so this is the next level up. So I had this beer the other day. It was really good. And I don't know, just about the generalized linear model is like a robot. I don't know. So if you've done enough statistics or talked to enough statisticians, you hear about linear models all the time. If you're like a neural network person, people like me are always saying, have you tried logistic regression? And you get really annoyed. And you go, why does people talk about linear models all the time? It's so annoying. Don't they know that we have nonlinear models that are very powerful? So if you have a machine learning background, how many people here do a lot of machine learning? Or any machine learning? Okay. Yeah, any made it a lot. Okay, great. So you're probably thinking, I know logistic regression. I know linear regression well. It's a toy model. You use it to show these things work, and then we get random forests, and then we just build GANs, and it's great. This is a very different view of how linear models work, and we're gonna think about them quite differently. And we're going to focus on different things about them. In fact, actually, we don't care about the predictions, which are like, what? There's not going to be any cross-validation in this section. And the cool thing is, though, once you see what you can use linear models for, you'll be like, that is basically all of statistics. I feel really cheated that they made it sound so hard. This is why you will know it all. So yeah, we'll get into linear models right away, I believe. So we're going to import a whole bunch of stuff. OK, so in case you're not familiar with the linear model, everyone who did high school math should know this. Should bring back like terror of like, I know, I see this, think of algebra, oh my God. Whoever met like rise over run, intercept, that's the linear model, right? The linear model just says like, we've got some slope m, we have an x, which is some value we care about, and we have some intercept b, and that's a linear model, right? Everything's a straight line, great. So we're actually not gonna use that linear model. Oh, I like this example. I have a long post on this. We're going to use logistic regression, which is an extension. So when I talk about it, you may have heard of the generalized linear model before and go, what is that all about? It turns out that, first off, the linear model is really useful, and we'll see that in a second. It's useful in a lot of places. And then you can do a lot more magical stuff with the linear model by generalizing it. And what that kind of means is you just bend its space. So this is, if you've used a sigmoid before, logistic regression, you've seen that S, right? And like someone probably put a bunch of like complicated equations and said this is an S, so we force these values. But all that's doing, this is the exact same paper I drew that one on, is it's bending the surface that we're looking at. So underneath you see it's the same linear model, it's just warping that surface. So that's what logistic regression is. That's what the generalized linear model does. It looks at a bunch of different ways we can use a mathematical function to warp the surface that the linear model lies on so it behaves in a very nonlinear way. So when you see that S, and it's often said always so it squishes values to 0, 1. That's not really true. You can actually, in the post I have linked there, you can derive it from Bayes' theorem and sort of see where it's coming at and understand exactly where this warping comes from. But another way to think about it for this example, for today's talk, is we want to deal with probabilities, not numbers that go between negative infinity and infinity on a straight line. So we're going to warp the space using a function. We're not going to go into that function, but that's what's happening. So we're going to talk about things as if they're on a straight line, but a straight line is going to be that one that I've bent right there. And we're going to use that to do all kinds of analysis. This is just so the linear model works with probabilities. This is logistic regression. And in our case, that just lets us do linear models with probabilities, which is great. OK, so we can now think of our problem a bit differently. And this is a pretty cool thing, but this takes a little bit of like cognitive leap. So I'm using like the high school math notation. Usually you use betas because it makes you seem really sophisticated. But then we have the beta distribution. It's very confusing. So you'll see all kinds of variations on how to write this. Don't be intimidated by them. If people put it in a format used for matrices, it looks almost exactly the same. So we can assume that these are whatever. This is the high school math version. So we're just trying to predict. And again, we're in this bent space. So these are going to be probabilities. But this is how we should think about the problem. It makes it a lot easier to decompose. So we just want to think about this. OK, so someone purchased it. And this is a logistic regression problem. If you've done logistic regression, you can think about the data this way. We have an indicator that it is or is not luxury, right? So this is like the simplest data science problem you could think of, right? We have a list of someone purchased it as our Y. We have a list of whether or not it's luxury. That's not that complicated of a problem. What our model is going to learn is these two coefficients, right? M, which is the slope, and B is the intercept. And we'll get into how to interpret those in a second. So we're going to build our toothbrushes up again. And this is just some code to restructure them into a data frame. So they're sort of in your typical data frame view that you sort of have. So if you've done a lot of linear models or any kind of machine learning work, you're very familiar with sort of like columns, prediction value, a bunch of columns. OK, so so we know what the A/B test data looks like. We've seen this before. So this is PyMC3. I'm not going to go into the details of PyMC3. All that matters is this little, I can't step out of the box. All that matters is that this is the equation we talked about. It's written there in that string. So purchase, squiggly line. This is R. I must confess, I actually read a lot of R. This is how you write it in R. But this is literally the equation. That one just means we want to learn some intercept. And we have some variable is luxury in our data frame that we're going to learn. And what we're going to do, and this is an interesting model. So one thing to think about with this, I don't think I actually wrote this down. I kind of wanted to. So one thing to think about with this is that the way this math works out, right? So we're going to learn some intercept, some B, and is luxury. Well, is luxury is binary, right? So it's either 1 or 0. And when we think about how this math is, it's going to be some number times 1 or 0, OK? I can write this here. I'm really excited to get to use the whiteboard. I love whiteboards. So when you think about what this is going to do on this thing, right? So we're going to have some Y, which is our purchased. And it's going to be equal to some intercept, some coefficient M, right, times the is luxury. I'm just calling it is lux, I don't want to write, plus some B, OK? So the question that might not be obvious here is how are we going to learn about the regular toothbrush and the luxury toothbrush from this data? So whatever number this is, right, and in this case, negative is bad, positive is good. I'll explain that more, but that's in general that number. The number that comes out of this is going to be kind of hard to interpret right away. But this is just a 0 or a 1, OK? So whatever this number is, let's say it's negative 10, right? Well, if it's not luxury, then it's 0. We don't care about this, right? And then all that we're left with, the probability of predicting is just B. So this B is going to be related to a regular toothbrush. Because if it's not luxury, it's like regular. And if it's not luxury, this thing gets canceled out. And so when it is luxury, it's just going to be whatever this is times 1 plus B. So this seems like it's kind of doing this fancy thing. It's really, really just switching these things on and off. And so what this is going to learn, this is luxury, this model, the coefficients going to learn here, this M, is going to be how knowing whether it's luxury changes the outcome. So that's why if this M is negative, it means knowing that this brush is luxury changes the probability down. If it's positive, it means it changes it up. So these are going to be in this bent space. So we're going to have to turn them back to probabilities. So they're going to be very large numbers, so much larger than 0 or 1. But in general, that's the logic we're doing here. And then we're going to learn this intercept. This intercept is actually going to correspond to how well the regular toothbrush sells. It's actually OK if this is negative. It just means that that's a low rate. But that doesn't mean anything bad in itself. If this M is negative, it means that knowing it's luxury hurts your probability that you're going to sell. So it's a very different way to look at the problem than the beta distribution. And initially, it's going to seem kind of annoying. And also, it's not clear how we're going to get certainty out of this, right? We want to know this distribution of our beliefs. So that's why we have PyMC3. Stan does the same stuff. So, and there is a Stan talk today. It's going to be great. So, OK, so we run this model. And what this is going to do is this is going to try and learn these coefficients. OK, and it's going to learn it by sampling. You can see it's the no U-turn sampler. The math behind this is actually quite cool. So how this works is really interesting. I definitely can't get into that today, but this is really, it's what PyMC3 or Stan both do under the hood is they take that simple equation and they're gonna learn a huge complicated function. No, this wasn't gonna be that huge, but they're learn a function that represents the space where the answer could be, and they're gonna literally sample from it in a very efficient way. And this can handle very complicated models, but it's all just sampling around that space. And what it's going to do is it's going to sample that space to come up with its estimates for what these coefficients could be, what m and b could be. And m is going to be called intercept in this, and b is going to be called intercept in the results, and m is going to be called is luxury. So don't worry about this area. This is sort of a diagnostic tool, because when you do these complicated sampling things, you have to watch out for all kinds of issues. But basically, these are what our estimates look like. And again, these scales are kind of tricky because we're not in probability space. We're on that bent piece of paper still. So the numbers look a little weird. We're going to go back, don't worry. We're going to take that paper and unbend it. But you can see what we have here is we have these distributions. And so we have this intercept where we have all these possible values for what we believe it. This is what the sampler found. And we have is luxury, which is it. And you can see this is a great example because look, this is 0. So for this one, if it's greater than 0, that means knowing it's luxury has a positive effect on the rate of sale. Right? Because the baseline is what the regular toothbrush sells. That's what this intercept is. That's going to be the regular toothbrush sale rate. Again, these numbers are in some other space. Don't worry that that's negative, and we're going to transform them in just a second. But if his luxury is positive, that means that the luxury toothbrush actually sells better than the regular one, because knowing that it's a luxury toothbrush means you believe it's more likely it's going to sell. So we can see a similar kind of structuring of the problem we had before, but with this linear model. So we can do the same sort of sampling. So this is to get values of is luxury. We'll sample that. And again, we can compute the actual probabilities here. This is a different run of the experiment. So don't think about this result compared to what we did in the last notebook, because this is all new data here. So in this case, we look at this and we can actually compute the probability that luxury is better this way. But it's still hard to reason about this because we're in this what's called the log odds space. It's just a bent paper, and it's kind of annoying to think about this. So we have a great, and we did this. So what we're going to do is we're going to take this and we're going to use the logistic. That's why it's called logistic regression. We can take this space and we can actually re-warp that paper back in. We can take these distributions and put them back into what they look like as probabilities, which is what we just talked about for an hour. So that's what we want to see. So again, walking through this sort of equation, we want to start with the log odds that the LO is for. That's the space that we're in. So we're going to get the samples for the intercept, which is the log odds of the regular toothbrush. The log odds of the luxury toothbrush are the log odds that it is luxury plus the log odds of the regular, right? It's a little confusing, but we're just taking these two we're combining these back, so now we're going to get a distribution of what our estimate is for the luxury and what our estimate is for the regular. Does anyone have any questions on this part? No questions? That's great. Okay, so we're here. But we're still in this annoying space. But we can use this logistic function, which will turn us back into probabilities, and we get this, which is really cool. Because this looks very familiar, right? It looks almost like our beta distributions we had before. And if we took, and again, this is another round of the experiment, so the results are not the exact same ones we had last time. If you look at the results from the same beta distribution, so this first graph is our linear model's results. This is what the model estimates for what it thinks the rate of sales for the regular is and the rate of sales for the luxury. If we were to redo it with beta distributions, this is the distribution we get. Almost exactly the same. Yes?
Why are we adding the log odds of a regular toothbrush to the difference in the luxury?
Yeah, that's a great question. I'm glad you asked that. Yeah, so because and this is where the linear model formula comes in, right? And this is where I think about and it's also important for us to think about what these values are. So if it's not luxury, right? So is luxury is an indicator. It's a 1 or a 0. That's what it's represented as. If it is not luxury, then this is 0, and it's going to cancel out this m constant, right? This coefficient here, right? And so we get this. So this base thing the model is going to learn is going to be whatever is not luxury, which in this case is regular. Okay, so it's going to learn some baseline. So what the model is actually trying to learn, the model doesn't know about the regular toothbrush at all. The model is just saying, okay, when it's not luxury, we know that means it's a regular toothbrush. It's going to say, this is the rate I'm going to try to learn for that. because when it's not luxury, this is 0, and then I don't care about that m at all. The slope doesn't matter. But when this is 1, right, this variable, it's sort of poor naming on my behalf, because this is also the coefficient name. When this variable, so it is luxury in this chart, and that's actually, I think, poor naming on my behalf. This is luxury is really the m, not the variable. So that's actually very confusing, and I apologize for that. So when is luxury, when this variable is 1, meaning that it is the luxury toothbrush, this coefficient is going to be just what it is, right? And it's going to be added to this base rate, which is the rate of the regular. So what we're learning, and this is how we have to structure it for the linear model to work, we're learning the difference between the two. So if we want to know how well we could just look at the difference. I mean, if you actually wanted to ask, can we just look at the difference? That actually would be totally fine to just look at this and say, this is actually all I care about. And that's fine too. But if I want to estimate what the model thinks the luxury toothbrush is, I have to add what its estimate for that is to its estimate for the regular toothbrush.
Okay, but since we got data that said that the customer bought the luxury toothbrush or not, why do we have to find it?
Oh, I'm sorry. That's something. Yeah. So actually, let me show you how I represent the data. That is confusing. Yeah. So I kind of went over that very quickly. So I went back and took the data, and we can think of it this way. Oh, I'm sorry. The question was if we're only looking at the luxury toothbrush, and but we're actually looking at both toothbrushes combined in this data set. So the data frame is going to have like a y and then an x, and the x is going to be whether it's luxury, and then this is going to be whether they bought it or not. Okay, that sounds good. That looks like good synthetic data. Let's draw some lines there. So this has only got 2 pieces of information in the model, and I really should not have named the coefficient the same thing as the variable. So that was very poor naming on my behalf. So yeah, so does that help a little bit? So this actually has, rather than separate the data, we put it all into one single thing for the model to learn. And that's what's different than when we did the beta. When we did the beta distribution estimate, we looked at each data set separately and came up with 2 separate parameter estimates, and we use those. In this case, we pushed all the data together so that this is just the outcomes for both. So it's going to, so if there's 30, if each thing got shown to 30, we're going to have 60 rows in this, right? Because we're going to combine all of the rows for the one that was the regular toothbrush. And the regular toothbrush is just going to have a 0 here. We don't need to have an encoding for regular toothbrush.
Okay, that makes sense. But what is the B? What is the data that you're adding? I mean, I understand that you're moving the values for the regular toothbrush
Yeah.
from the slope, and then you're adding a constant to the end. But why are you adding back in the regular toothbrush log odds?
Oh, so the regular toothbrush log odds is just this B, right? So let's go back to this little thing.
Oh, yeah.
Yeah, so I'm just getting the values for the intercept. So it's the estimates for what this is. This is actually, it's going to learn that distribution for this. We're just taking these samples for what it thinks this could be, right? And we're adding, because we ultimately want to get the probability of y, right? This represents the probability of y. And so this is going to give us a distribution. This is going to give us a distribution. So yeah, does that?
So, I mean, basically what you're saying is for 10 there, the log odds of luxury is equal to m plus b.
Yeah, exactly, yeah.
It's just that.
Yes, that's correct, yeah. Yeah. Oh, he just said that the log odds for luxury is m plus b. M plus b in this form is the log odds. That's right. Yeah. So if we look at this, then yeah, m, because this is a binary indicator thing. So this is going to be either cancel m out or not. So the log odds for luxury is just m plus b.
Right. So it almost seems like 9 says the log odds for regular is equal to b.
That's right.
And the log odds for luxury is equal to m plus b.
That's correct.
Right.
That's correct.
And it's just the.
Separating the regular log odds when you're doing the analysis, and then you're adding it back in.
Yeah.
Okay, that makes sense now.
Okay, great, excellent. And definitely, because linear models are tricky. Like getting this in is actually like, I mean, the cool thing is this is a powerful tool because you can use it for all kinds of stuff. But actually, yeah, these transformations are non-trivial. And thinking about the results of your experiment, and especially for this problem, you're going to go, why in the world would I not use the beta distribution one? That was a lot simpler. This is a lot trickier. Just to wrap your head around, I agree. It's a very sort of like, okay, what's going on? But so the interesting thing I want to point out now, so if we go back and we did this the beta distribution way, right, the parameter estimation way, this is what it would look like. It's almost identical. It's mathematically also almost identical. It's always almost. So anyone that's really a rigorous mathematician in here, if I said these are identical, they'd say that's not true. You can prove it. The Dirichlet and the logistic normal are not the same, but they're close enough. And they always will be close enough. So this is a really cool property to have. But again, this seems like a mathematical exercise to do this. Why in the world do we have to do this mental contortion to get our data to fit into a linear model? But we will show you. So, yeah, see, why do I care? So we have two pencils now. A very nice pencil and a deluxe pencil. You can tell the difference because one has got like a blue and the other one has red. Not very different. It's part of the exercise. So, and they're not very different, right? This is the very nice pencil and this is the deluxe pencil. And so the deluxe pencil is slightly worse quality, slightly lower price. Based on what we've seen so far, we should kind of believe that the deluxe pencil is probably going to sell better, right? Because we've seen that people tend to be a bit more price sensitive than they are quality sensitive, just sort of looking at this. And we want to run a test just to make sure this. And so we run this pencil test, a pen test, I guess, for security people. But and then we get a whole bunch of samples here. We get a whole bunch of samples because the linear model really likes a lot of samples. So we do this and we get something that's kind of annoying. So in this case, let's make sure we got this right. So the very nice pencil is A, the deluxe pencil is B. The very nice pencil is a bit more expensive, but a bit better, very bit better. And the deluxe pencil is cheaper. So we run this experiment, it should be good, but we get this kind of confusing results. We have 2,500 samples, and something is not quite right here. We're getting a better estimate for the toothbrush that does not make sense, right? That's toothbrush, pencil. The A pencil costs more, and it's only a bit better. And it doesn't, based on what we've seen, I'm not really comfortable with this result. So something seems to be happening here, right? And if we wait. Oh yeah, so we learn this in the linear model. We can repeat this. This is just, again, putting this data into a data frame. We're repeating the last experiment over again. And we get this, and yeah, it's not like just, maybe it's an uncertainty in our estimate, but if we build this linear model, we run it again, it's built the same way this is, right? We have a is deluxe pencil, we have an intercept, we get this, and we go, geez, I mean, none of that is really over 0, so it looks like we're very certain the deluxe pencil is worse. This is actually a good part of your statistical thinking. You should always have kind of like a sanity check in your head of what you think the world should look at like, and if the world doesn't look like that in your statistical test, you should ask why. Never ever like look at the output of a model and be like, well, the model says what the model says. We're done. Statistics, right? And then you see that happen. That's why we have the reproducibility crisis, right? You should always be critical. Statistics, because statistics is based on logic, it should always be a logical argument. It should convince you. You should be convinced by your analysis. And so when you see something like this, you go, that does not make sense. Something is wrong here. You should dive deeper rather than just saying the p-value is really low. I'm done here. So you could say that here, but then you'd be wrong, because I know what happened, because I designed this experiment. So, and you notice we actually used when we ran this experiment, I had a messy experiment class, so that should be a clue that something is not quite right here. So we ran this, so this statistic has failed us at this point, and we're certain that it's not right. So but if we look at the customers, so this test also keeps track of what the customer types were. We realize that we have this not great, it's not all just regular customers, we have these student customers in here. Right? So if you look at the customers that visited A, we got some students in there. And if we look at the customers that visited B, we have some students there as well. And it's not obvious here if they are different, but we can go ahead and count that up. And there's a lot more students in the B group. So our test was not perfect, right? We showed these pencils to people. These are relatively expensive for a pretty mediocre pencil, if I say so myself, but it's high quality, so I guess it's good. But so this isn't great. Now, if we just have the beta distribution, we go, what are we going to do? We can throw out some data. Maybe we could try to balance these out. Maybe just throw the whole experiment out. But this experiment has gone wrong. But we have this information. We know who bought it. We know whether it was students or not that purchased it. And it's a pretty reasonable assumption to say, Well, I think students probably have a lower price threshold than an average consumer. If a bunch of students come into a SaaS website that you're running and you're trying to sell expensive software, it's not shocking that you're going to sell less if it's got more students. But we know there's students. We have some information about this problem. This is really helpful. So we can go ahead, we can get this data, and we're going to concatenate this into a data frame. So our new, we have an eraser. It's very rare to have whiteboard markers that work and an eraser. I think this is good job, Microsoft. This is a good job. So we're making something a little bit more complicated now. Okay, I didn't write this out. The nice thing is you don't have to always write these out as equations, but I think it does help. And I have a whiteboard, and I'm going to use it. So what we're going to do is we're going to make a new data frame where we have our y, which is whether we purchased it or not. We have is deluxe. I really should have named these coefficients different, but once you do linear, the reason why I made this mistake is once you do linear models enough, you kind of internalize this thinking. You go like, I know I care about the coefficient. I'm just going to name the column the same as the coefficient, and you do that. So we have is deluxe, and we also have is student. Is student. So we're going to have this indicator. It's exactly like the last one, indicating whether it is a deluxe pencil, and we also now have this one that will let us know whether it was a student. So this is actually pretty cool. So now we have a bit more information, and we have the same property because it's this binary indicator, right? And this is a pretty common thing you'll see when you're doing statistical tests, is sort of you just know whether something is true or not. And it has this nice property that the term drops out when it's 0, which is super convenient, right? So now we have 3 things we're going to learn. Well, and we'll also have the intercept, which is going to tell us something about, well, we're going to learn these things. We're going to learn the intercept from this. So we're going to learn some coefficient for is deluxe. And we're going to learn some coefficient for his student. And we're going to learn some intercept. And the intercept is going to be the rate of what happens when the pencil is the very good pencil, very nice pencil. Is deluxe is going to be the difference from when we know is deluxe pencil. And student is going to be the difference when we know it's a student. So we're going to learn 3 things this time. And you can think of how these are all added, right? If it's not deluxe and it's not a student, we just get the rate of the very nice pencil when we try to sell it. If it is deluxe, but it's not student, we add this and this, and we're going to get the rate of it being a deluxe pencil selling. If it's deluxe and it is student, the student's going to tell us how much the student's impacted this. And so what we're going to learn is actually a whole bunch of stuff, which is really cool. I'm just going to run this so you can see it. So you can see here's our thing, here's our equation, right? And yeah, actually, that is why I named them this way, because now I think about it, it actually is confusing for learning, right? So those are the column names it's going to look for in the data frame. So that is very helpful to have the column names be the coefficients, but they're really it's the x is the data frame column, and the coefficient is separate things. So that's interesting. I never thought about that. So we're going to run this, and we're going to get these, which is really, really cool. So the intercept we really don't care about, because that just tells us what the rate is, our estimate for that rate. And is deluxe is now all positive, right? So we're not going to convert these back into, I don't believe I do. Yeah, we're not going to convert these back to log probabilities. We don't have to for this one. But we can see that because deluxe is all positive, it being the deluxe toothbrush, as we suspected, is entirely a positive impact on its sale. And the students, we have this sort of broad distribution there, but now we have this estimate that the students is all a negative interaction, which makes sense. So now we've been able to take this linear model, which extends what we did with the, when we just did it to replace 2 parameter estimates, it was annoying to use a linear model. It didn't make any sense. But now, this little complexity in our experiment design, we can now resolve it. And the cool thing is we actually learned, not only did we uncover that the deluxe toothbrush probably is better, right? Now that we've been able to account for their student population, we also now have information on, well, how well do students purchase pencils, right? This assumes, one catch in this, right, is it assumes that the student purchasing behavior is independent of the actual pencil itself, right? They just have some sort of fixed rate that they hurt sales. But out of this now, we had a test that looks like it was a flawed test that we had to throw out, but now we actually got all this information about how students behave as well. So we have estimates for it. We know the deluxe pencil is a bit better because, as we expected, it's a bit cheaper and it should be better, and also that students are worse. And we could go ahead and throw these into we could transform them logistic and do the beta distribution on these and see what that is. So this is the very, very beginning of what you can do to generalize linear model. But yes, yeah, question.
Yeah, so I sort of understand about what, the linear aspect of when you were doing with one is deluxe.
Yeah.
When we threw in the second binary,
Yeah.
is this like linear in three-dimensional space or something?
Yeah, no, it's a great question. I mean, I think you're right. Yeah, it is drawing. Yeah, you're absolutely right. You are learning this much more complex thing, right? Yeah, because we can think of this as we can think of this as a vector, right? If you did this like in machine learning, we would put this as one big X, and we'd have these coefficients, and we separate them out so it's easier to read. But yeah, we are getting into this sort of multi-dimensional situation. And if you're asking, does it get complicated there? Yes, it does. Like you can definitely get. Already, it is tricky to sort of figure out what's actually happening, right?
So as we add each Boolean here, we're basically going from two-dimensional space to some 3D, possibly ND.
Yeah, well, it's still.
Linear is in that.
Well, what still is linear. What's nice is it still just gives us the rate, right? So the ultimate thing is, what we're getting is, so when I put that y there, we're really learning the probability of that purchase, right? That's ultimately, we're learning the log odds of the probability. So when we remember that, when we just solve the equation for whatever information we have, the answer that gives us is the log odds, or a transformed version of the probability of y. We can draw more. We can draw more on the whiteboard. Yeah, this is really tricky. And we actually we're done, and we still have 10 minutes. So.
I mean, is another way of looking at this as like a decision line, where everything above that line that's cutting across means that it's better to be, luxury wins versus non, or in this case, it's like a plane, and it's almost like.
Yeah, I wouldn't actually worry. I mean, actually, you can. So let me just write this out, and then, did you have a question, real quick? Is it?
Oh, I was just going to ask you to explain the syntax of the formula we put in again.
Oh, this formula right here. This syntax. Oh yeah. So this is like shorthand for the. So yeah, so in the data frame here, in this pencil test data, there is a column called is deluxe. There's a column called purchased, and there's a column called is student. And the 1 just means I care about the intercept. I do not believe you need to put the 1 there. It will always add an intercept, but the 1 is just notationally there. So is that correct? I see you shaking your head. Yeah. I always put it there because I want to make sure that it's there. So
what does the 1 mean?
it just means that we have an intercept, right? It's going to learn some coefficient times 1, and it's always going to be 1. You don't have to put it there.
Okay, so
It'll do it for you.
Equation.
Yes, exactly. Yeah. So this is yeah. I always found this. I actually found our syntax very confusing. Yeah. So what that is it's tricky because it's this string, right? So in the data frame there, and this will actually, as I write this out, I can help answer your question at the same time. So this is a great combined thing. Yeah. So this is, and you'll see this a lot. This notation comes up in R a lot, and this way really helps sort of stretch these things. So in pencil test data, we have a purchase column, is deluxe column, and is student column. So what we're learning is I can't spell. Okay, good. I was awful at spelling in like all of grade school, and I thought that would not be a problem as an adult, but it's like #1 coding error I've ever had is typos. And I really feel like I can't believe that like primary school was right. So what this actually is confusing notation. So it's going to learn a coefficient for each of these, and just like me, it's going to name them poorly. So I'm trying to think notation how to make this more sense. So these are the values that are going in, okay? You can think of this as the values, right? So there's a 1, which is going to be just all 1s, and it's going to learn some m0 of 1. It's going to learn some coefficient m for the 1. The squiggly just means equal, because we don't want to use equals all the time. It's just a convention. So the squiggly looks very magic. When I first saw the squiggly, I was like, well, what's that squiggly all about?
Oh, so squiggly is equals.
Yeah. Or to be fair, if we want to be really technical, right, we could talk about the squiggly kind of implies that it's being sampled from this distribution.
Sure.
So it's not, there is, all right, so yeah, I shouldn't say that you can ignore the squiggly and equals thing.
Separating it from the right.
Yeah, exactly, yeah. Yeah, and the squiggly actually does often in notation mean it's being sampled from some distribution. So it is. I do want to correct that. Don't just translate that as equals for weird reasons. The reason why is that you can, if you use more and more stan or PyMC3, you'll see that squiggly, and that squiggly usually means especially in notation, it means that it's coming from so it's squiggly like normal means it's coming from a normal distribution. It doesn't mean that it's a fixed value. So there's some distribution of parameters here. That's a lot to dive into, but for thinking this through, that's where the equal sign goes in your equation. So yeah, so what is happening under the hood is it's going to learn m0 times 1 plus m1 times is deluxe. This is my time, my dot. Is deluxe plus m2 times is student. So the reason why it's a 1 is 1 times, it's always going to be 1 times this coefficient, which is the same thing as just having that. That's why this is going to be the intercept.
M0 was the B?
So yeah, this is going to be B, yeah.
Okay.
Yeah, so it's learning these as each coefficients, but when you think about this, B times a constant value, it's always going to be the same, right? It has no, you're just going to learn some consistent thing there. So that's what that's going to be. And then, so for this, and this gets, so this is, and then I have a blog post that does go a lot more detail, but this represents a linear version of our probability, right? So this is not actually a binary at all. This is going to be some number that, when we do the logistic, gives us the probability of purchased given the data we have, which is a bit more nuanced. So you're actually learning a probability of purchased rather than a binary purchase. There's not a threshold here. So you're going to learn these coefficients. So if, in the case where, this is always going to be 1, right? Because there's no data being input here. When it is deluxe and it is a student, this is going to learn, it's going to multiply whatever the penalty for being, or penalty or reward for being as deluxe is, plus the penalty or reward for being a student, right? And you add them out and you're going to get this, and you're going to transform it, and it's going to give you the probability. The only reason we have to do this annoying transformation is because otherwise it wouldn't be linear. So we need to have that. That's the generalized linear model part of it. But basically, this is going to be this is going to represent how much this hurts or benefits. And you can keep going forever, right? You can add more and more and more things. The tricky thing is, this is where it's a linear model, and just like with a regular linear regression, you have the sort of weaknesses, right? Where you can see them more easily in a traditional linear model. But the issue is this model does not account for the fact that maybe students really like the deluxe pencil for some other reason, right? This model assumes that students buy pencils at a lower or higher rate independent of everything else about the pencils. And so that's something you have to keep in mind, especially for experiment design. So if this deluxe pencil said, like, I hate students on it, then this is not really going to be correct, right? If there's some reason why students would be like, oh, I don't want that. It says it hates me. Yeah, right, exactly. Yeah, this is not the pencil I want. So there are all kinds of assumptions in here. So, but this is a framework. When you think about this, you can start asking all kinds of more and more complicated questions. You could have a whole bunch of demographic information, and then you're going to get estimates about all the demographic information, which is pretty cool. So, and again, this is where if you're a machine learning person, you're like, wait, we don't even care about this? We don't care about the outcome? You can, right? If you're trying to like come up with some risk you want to have, right? If you want to have if you want to be like, what's the, we want to put a promotion on the website, but only if there's a greater than 20% chance that the person's going to buy the product, right? You might want to do this. One of the homeworks actually is, so these are discrete things, right? These are binary things. We've seen that we have this quality and this quantity, right? So we could think about this problem a little bit differently. We could ignore all these other things we've seen, and we could generate a whole bunch of products, right? And we could say, okay, given its quality and its price, learn some coefficients there. I'll take that too, right? And now you actually have this model that says, okay, I need this to sell twice as much the rate. This is where these things get really interesting, right? These get really powerful. And this is when people talk about interpretable models versus explainable models. This is an interpretable model. Because if you modeled price, let's say a whole bunch of products here, right? We've just seen the toothbrush and the pencil. We know that price seems to be more important than quality. We don't know exactly how they work, but you can actually start learning exactly how they work. So you could generate, in this example, or in real life, take the products you have with a whole bunch of different prices, right? And you can say, did it sell or did it not, based on just its price and its quality. And then these will give you how those affect things. So you might say, I need to, you can answer it really, and this is like one of the homework questions, is you can answer questions like, I need to sell 20% more of these. I know that price has an impact on this. If you can learn exactly how price has that impact, you can learn exactly how you have to change the price to increase the chance that it'll sell by 20%.
So what would the syntax of that look like?
Yeah, so yeah, exactly, yeah, great. So the syntax of that, so we'd have to have a data frame that had purchased and quality columns, right?
Yep.
And it's totally fine if they're numbers. So that would be, let me look so I don't mess up. So yeah, there's the purchase, that would be, if we have that data frame we pass in that has those things, it's going to be, this is my quotes, purchased, squiggly, tilde, 1, you can put the 1 anywhere, I believe, 1 plus, I don't know why I'm looking there anymore, price, whatever assuming that price is the data frame column for that, and quality. And these actually would be continuous values, which would be interesting because it will. This is where you get into all the complexity of linear modeling because you might say, well, Will, you told me these can be between 0 and 5. Well, now it's a different problem. But if you assume these are sort of both continuous things, you could even. So this would be it. That would be all of it. To answer your question, that would be that. And then what you get out is you get distributions for both of those, and you could see. And again, it's hard to interpret those distributions. But getting back to what you were saying, you could go in and say, okay, so I have a thing that I know is a 5-star quality item. And it's currently $20, and it's not selling. So you can put this in, put that there. You're going to get a distribution of what the rate of sales is based on what you've learned for that particular thing, which is kind of cool. And then you could say, what if I made it 18? How much more would it sell? You could actually make that 18, recalculate this, and you're going to get another distribution of predictions for that. Or you're going to get a point estimate, but you can get a distribution if you want. So this stuff becomes really powerful. And that's where, like I said, when people go on about interpretability, then this is inference, right? So when you talk about there's prediction in machine learning and there's statistical inference, and this is the inference problem. And you can see what we're doing is we're kind of reverse engineering reality, right? We're really trying to figure out how things work, and we have to use these simple models, right? This is why, if you're talking to a statistician and they're like, why don't you just use a neural network? It's because you can't make a model using a neural network that makes sense to you and me. Right? So for certain problems, we have to do that. Like, I don't really know how language works. I don't think language works as a linear model. So we use machine learning to do that. But for these type of things, especially for like regular business problems, this is the kind of logic we want to use because we want to say things like, okay, at Wayfair, actually, one of the big problems we have is we want to show products more and see if that helps them sell more. It doesn't always work. So you can actually see how does that work. Like you can actually model, I run experiments where I model these things as more, you can actually model interactions, which I don't want to get into, but you can multiply 2 of these things and then actually tell us how they interact with each other. So if you wanted to see if students buy a pencil differently because the deluxe pencil is mean towards students, you can actually put that in your model and learn that. There's really, really no limit to how far you can go with this stuff. But of course, as you get more complicated, you run into more problems and there's more catches to everything.
So one of the issues is that each of these components need to be independent.
Yeah.
So if you have a situation where people look at the price and they assume that it affects quality.
Yeah, exactly. And I don't want to get into this, but this actually is another question. If you wanted to model that in this notation, you can. You could do plus. There's a great book called Statistical Rethinking. If you want to go really deep, it's in R. But there's a whole Python set of stuff, and he really covers this much better than I ever could. It's a really excellent book for going into details of this stuff. Price times quality. This is going to be really tricky because it's going to. Don't do this at home yet. Read more about it. But to answer your question, this would actually do this. So this is going to learn a coefficient for these 2 things times each other. I believe that's correct, right? Yep. Okay, good. Thank you. I wasn't sure if you actually had to pull that out. Yeah. So what you're going to learn is you're going to learn a 3rd coefficient, which is the interaction of these 2. Now this is tricky because you're learning how price affects it, how quality affects it, and then the way price and quality work. So maybe you want to get rid of some of these and just learn this interaction. That's going to be kind of weird. So there's a lot of different ways you can do this. It gets really complicated. And then this doesn't even touch on the true power of like Bayesian inference because you can learn even more about how all these things interact. There's no limit to this.
So the coefficient of the price times quality,
Yeah.
if it's not 0, then we're saying that they're not independent, or what's?
So actually that gets a good point. So at the very least, if it hovers around 0, you could say these things aren't related. How you're going to pick that apart when it's not 0 is not easy. The typical advice is to actually, and this is way beyond the scope of this talk, but you can actually sample, since you have these 2 distributions, you can run the model backwards and get uncertainty about all of your estimates. But if you want to know when these interactions appear, you really have to sample from the data to sort of get a feel for how it's doing. It really is hard to just interpret. So for these simple ones, you can do, for testing purposes, these sort of simple things like, this is actually this is more complicated than you want to do on a test, right? This is giving you a lot of information. But in this simple case, you could at least say this hurting, and you can see which is more important, price or quality. Obviously, from what we've seen, it seems that quality is less important than price. It seems to be the big push for people. So, and this model would probably learn that. If you sampled from enough examples of things that had different prices and qualities, the model would give you estimates for these. And my guess would be that this coefficient would be, in general, lower magnitude of an impact than this would. That price is going to have a more strong impact on the sales. Oh, we're at 10:30. Thank you. I have a blog too, Count Basie, and I wrote a book on this stuff. So, and I wrote a Haskell book. Thank you so much.